Hello, this class is going to be on how old, and really it's determining how old things are and how do we actually know. What are the various methods for determining how old things are? And so we'll begin. I'll point out that this video is being recorded without any pauses because I can find no way to actually pause this. So there may be some errors or flubs or things like that along the way, but you'll get the gist. Uh, so we're going to start with this one. This is me. And this is a multiple choice test on how old am I? A, B, C, D, E, F, G, H, I, J. Okay? Please take a moment to pause the movie and write down your answer. This is not a this is not going to be something that determines your grade or anything else. Just simply, write down your answer, and we'll talk about the process by which you thought through this. Perhaps there are some answers you can eliminate immediately. Perhaps you can only juggle a few of them, and so on. So I'll pause for a second, and then you can write down your answer. Okay, so we're back, and pretty much whatever choice you chose, that's going to be your grade for the semester, and that makes my grading a lot easier, and everything is straightforward. All right, so continuing on, we have the question of how you chose what you chose and how you determined your final grade in this class. There are some that you can probably eliminate altogether. For instance, A. There aren't going to be any A's in this class, but that's okay. And that's and you'll know because of things like size and somewhat how I look in terms of amount of hair and facial features and so on. You can also rule out I and J again for the same reasons. Things like wrinkles, things like gray hairs, and so on. So, what is it that you're actually doing? And this is something that you do every single day. Every time you see someone, you can estimate it. And possibly in some people, you can estimate within a few years. Some people, you can only estimate within a decade or so. And then some people look a lot younger or older than they really are. So, what are we actually doing? And this is the same process that we use to determine the age of something like the moon or the Earth or even the universe. So, what do we need? What we need is a process which changes in time and leaves some marker of the change. And from the marker and the understanding of the process, we can infer age. So if we go back to me, what we have is the process that changes with time are things like the growth and development of a human body, things like size and facial features, wrinkles, gray hairs, and so on. These are things that leave their mark and they change in time, and you're able to then determine or estimate the age of a human based on these processes. And if we the more we understand the processes, the more that we can determine age. And if you're very careful, you can do things like take hair samples or bone samples or things like that and determine age very closely. Most of the time we don't need that level of detail. So let's look at another example. And here we have a picture of craters from the moon. And we want to ask the question, which craters are the oldest? So we have a process which is essentially cratering, and it leaves its mark, which is the crater. And we have to understand this process. And essentially, we just have rocks of various sizes that crash into the structure of the object. Um, and knowing that process, we know a few things. One thing is we know that if we had a bunch of little rocks make little holes, and then we had one big rock come in, the little holes would like right on top, and the little holes would no longer be visible. So we can get an ordering of craters. For example, I'm not sure whether okay, there's no arrow here. Um, so the big crater in the middle had to have occurred earlier than the little craters that we see, and there are a few other instances of craters within craters or craters overlapping, and you can tell which ones are older, which ones are younger. It doesn't tell you whether they are older by a year or by a century or by a million years. It just simply says this one came first, then the other one came later. if we knew more details about the process, namely how often rocks of various size crash into a planet, we can estimate the actual age. There are also direct measurements, but we'd have to go there, which we have done for the moon, and I'll get back to how that works somewhat later. So let's look for another example. And this is not the Earth. But the question is, could the Earth be 6,000 years old? And this is a picture of the far side of the moon. And believe it or not, this picture of the far side of the moon demonstrates that the Earth cannot be as young as 6,000 years old. It must be much older. Now, why is that? Well, we can tell from the size of these craters and simply counting them up. And what we have is there are about 250 craters with a diameter of 100 kilometers or more. At the time that these craters were made, the Earth would have been just as likely to be struck by large asteroids. In fact, more likely because it would be larger. And so, if all these craters essentially occurred within the past 6,000 years, we can calculate out a cratering rate. That would be 6,000 years and 250 craters. That'd be about 24 years per crater. So, every couple decades, you're probably around 20, between 20 and 30 years old, so you should have experienced one of these in your history, which we haven't. And the Earth should be struck every couple decades by an asteroid capable of completely ejecting an area about the size of New Hampshire. Now, clearly this has not happened, and it has not happened in the past 100 years, and it has not happened in the past 10,000 years to this degree. There was one event documented in 1900, which blew away a large chunk of Siberia, a large area. I don't even think that was quite as large as this. But if it were this common, then these would be written in every single book, in every single civilization going back to the dawn of civilization. I mean, really, we would have seen this, but we don't. So these craters had to have occurred in the past, and it says that the cratering rates have drastically decreased in recent years compared to when these craters were actually formed. So this is one way to kind of reason from the process that we know, essentially, rocks striking the surface, and the fact that if that were the case, then the Earth would receive quite just as many, and the fact that we don't observe these things, and it infers usually in this case we can rule out certain time frames. 6,000 years is just way too short. But there are other ways that we can do this. We go pretty much to say geology. In geology, we have layerings of different types of rocks. We can understand the physics of how these rocks move around, how they're laid down, and so on. And in many places, especially for sedimentary rock, it's quite clear that the younger rocks are lower than the upper ones, although it can happen where you can get certain types of outcrops where you get the opposite. So actually, sorry, the younger surfaces, the ones that are laid down most recently, are higher. They're closer to the surface than the ones that are older, which would be deeper. So the deeper you go, the older you go. This is also like tree rings. Tree rings, the deeper into the tree you go, the older type of wood you're going to be looking at. So what this does is it gives you a timeline, and if you have an estimate for how long it takes how long it takes each layer to get laid down, you get an estimate for how old these are. Now let's change topics a little bit. Let's talk about stars and determining how old our sun is from various means. So here's the first kind of piece of the puzzle. We have different types of stars, and if we smear out their light into a rainbow, we get different types of rainbows. Sometimes some stars are redder than others. They're kind of dominated on the red end. Some are bluer than others. They're kind of dominated on the blue end. And we have these dark stripes that run through the entire sequence of stars, and these correspond to the patterns that you would see for different materials. So, for example, hydrogen, which is the most abundant material in the universe, has a has a line at about 0.65 micrometers here on the scale. You can see the dark line running through all the reds. It also has dark lines in the blue and the purple, and those are the main ones that we see over on the left. Helium would be the next thing, and it actually has some lines in the yellow, which is what you see, and also some of the lines in the purple and the blue. So we can tell the contents of stars. The actual color of the star, the dominant color, depends on temperature. So the cooler it is, the redder it is, the warmer it is, the bluer it is. And this can give us an indication of the type of stars. We could imagine the star being powered by, let's say, gasoline, and in this case, we would basically say that the mass of the sun is, we know what that is. 1 kilogram of gasoline gives me a certain number of joules, and I can know the energy usage of the sun by knowing how much energy, how much light it shines out, and how much energy I can collect at certain distances. So we know that the energy usage of the sun is about 4 times 10 to the 26 joules per second. The mass of the sun is 2 times 10 to the 30 kilograms. And if we imagine that this object is powered by gasoline, we would have we could calculate out the age of the star in this way. So I'm going to let you pause. I know we may have gone through this in the notes, and if not, it's good to go and review anyway. I'm going to pause this movie. I'm going to want you to write this problem out, and you'll be handing this in so that I know basically what is the age of the sun, assuming that it's powered by gasoline. And so you can write this. You can write this out. The sun is not actually powered by gasoline, and this is actually one way to demonstrate this, to show that basically the age does not make sense for the actual age of the sun. So how is the sun actually powered? The sun is actually powered by converting its mass into energy. From Einstein's theory of relativity, we have E equals mc squared, where the m is the mass and the c is the speed of light. This means that energy and mass are equivalent, and they can be converted between each other. So the mass through the nuclear fusion process of the star and the cores of the star is being converted into energy. So the sun is actually losing mass continuously. So if this is how it gets its energy, that will give you its total energy supply. So if you imagine the mass of the sun completely being converted into energy, that will give you a total energy supply. And then knowing that the sun uses it at a rate of 4 times 10 to the 26 joules every second, we can determine the age of the star of our sun this way. Essentially, not the actual age, but the lifetime, how long it lasts. And we could compare that to assuming it does it for gasoline. This is part B of the problem that I want you to do, and that is assuming that the entire mass of the sun is going to be converted into energy. How long would it last? Now, there are various details that occur that make it so that it's really only like a tenth of the mass that gets converted. And that's not even a tenth of the mass; it's a tenth of the hydrogen gets converted to helium at about, I think, about 0.1% efficiency. So it's a fraction of the total available energy. If it were all to be converted into mass, all of it converted into energy is used. So that number, when you kind of factor in the details, ends up being around 10 billion years. Your first answer for gasoline should be much shorter than that. Your second answer, which assumes all the mass, should be much larger than that. And the real answer with all the details is in between. It's around 10 billion years. So that's the next part of the problem. In order to talk about how stars change, let's discuss some of this nuclear fusion process. What we have here in this table are the masses of a number of different things: hydrogen, helium, lithium, carbon, etc. If you're very careful, and let's say you take 2 protons and 2 neutrons and you add up their mass, you will notice that their mass is a little bit more than the mass of helium, which is made up of 2 neutrons and 2 protons. A little bit of that mass goes to energy. So you can take neutrons and protons and slam them together and create something that has less mass than the combination, and that would be helium. And that little amount of mass difference multiplied by many, many, many atoms of hydrogen and many, many neutrons uh, would give rise to the feeling of our sun. And that gives us energy. Now, not all things, you don't gain energy from all nuclear reactions that go from small pieces to larger pieces. Here's a plot of kind of the energy that you get per kilogram going from hydrogen to helium, and you gain a lot of energy, and then from helium to carbon, you get a little bit of energy jump. So you really don't have much. If you were to try to go from, say, carbon to nitrogen, it would actually be a decrease of energy. It would take energy to slam carbons together to make nitrogen. And so we can go up. Essentially, the fact that this curve goes up and up and up until iron means that you can fuse the smaller elements, hydrogen, helium, carbon, oxygen, magnesium, and keep getting energy out of it, even though it's kind of diminishing returns after a while. On the other side, starting from the right, we have uranium and lead and others. And there, you can't join together smaller elements to create larger ones and gain energy. You lose energy. But you can do the opposite. You can split the large uraniums into things like lead and others, and gain energy that way by slicing them together, slicing them apart. So we can split uranium and get energy, and we can join hydrogen and get energy. Stars work by joining hydrogen and helium and so on, to bring up higher, heavier elements and gain energy. Um, Nuclear power reactors use splitting uranium and other large materials to gain energy going the other direction. Iron's at the top of this, which means you can neither fuse nor split iron to gain energy. It's kind of a lose-lose in either direction. And what happens for very big stars that go through a sequence of creating these heavier elements, eventually it gets to iron, and their nuclear furnace in their cores will actually stop. So here's kind of a stellar evolution for our sun. When it was formed, it was mostly helium and mostly hydrogen and then somewhat helium, about a quarter. And then in the core of the sun, the core changes to helium almost entirely, and this core is still not hot enough to fuse helium into higher, heavier elements. Once that happens, the core cools a bit and then compresses and then heats up again, and there's the ability to fuse helium into carbon. And so what you get if we start in the lower right hand corner of this picture, I'm just following the little diagrams of what the sun is. Starts off with a hydrogen burning core. When they use burning here, they're really meaning fusing. It's kind of a shorthand, and then they once the core fills up with helium, the outer part cools up and gets big, and this whole thing blows up like a big balloon. Eventually, you'll actually get our sun swallowing up the orbit of Mercury, and anything on the Earth would be cooked by that time if there was any living things on it. Also, eventually, the mid-center of the star would start fusing helium to carbon, and eventually the outside of the star gets blown away in a kind of a graceful expulsion, and it leaves behind the white dwarf star, which is just the carbon cinder of the kind of remaining, this hot carbon ball that then cools and cools and cools, and what is referred to as a white dwarf star. And that's the evolution for a star like our sun. If we want to look at bigger stars, what we get is essentially in the lower right here, we pretty much get this onion where we essentially have hydrogen fusing to helium, helium to carbon, carbon to sodium, neon, magnesium, and so forth, all the way down to an iron core, and then we get usually a stellar explosion. of one kind or another. If we Here I'm going to point you to A, the upper left-hand corner, and this is a plot of a bunch of stars of various masses. And it turns out that this is a plot of temperature on the x-axis, and notice it's hotter toward the left and cooler to the right, and luminosity, which is the total amount of energy being cranked out of the star. And what we see here is that there's an actual pattern in what's called the main sequence. So essentially, the larger stars are both hotter and more luminous. And because of that, because of they're much hotter, they use energy much faster. So even a star that is twice as massive as another one will be brighter by a larger factor. It'll use up its energy more quickly than twice. So that means that the largest stars they actually start dying first. So if we got a whole bunch of stars that were born together at the same time, and they had different masses, and we plotted their temperatures and luminosities, it would look like the plot on the left. As we watched this cluster of stars, what we would, if we were be able to watch it over millions and millions of years, what would happen is that the oldest stars would die first, the next, not the oldest, the heaviest stars would die first, the heaviest and brightest, and they would start changing into red giants, and they would cool off, and this is why you see it in B, peeling off at the top, and and so on. And then what will happen is that main sequence pattern will peel off and peel off all the way down, which means that if we can compare, if we happen to come upon a cluster of stars and we were to make this type of diagram, and we happen to notice that it looked like D, it didn't go all the way up to the very hot stars, we could determine the age of this star cluster. So the lifetime of the star and the determination of age are intricately linked in with the properties of these stars themselves. So our sun is pretty much near the middle of this at one solar mass, and then it will live for about 10 billion years, and of which we know that it's been around for 5 billion years. Now, how do we know that? Well, how can we tell how old the Earth is? Again, we need some process that changes in time, that leaves a mark in time, and that we can estimate. And we see some of it with geology, where the motions of the rocks on the Earth. We can see it with cratering that allows us to do it. And now we're going to look at how we can use radioactive decay in order to determine the age of these sorts of things. So I already said that you can gain energy from splitting larger atoms into smaller ones. And so, for instance, and what I didn't say though is that this happens spontaneously. So if you have a kind of brick of plutonium and you wait about 2.5 million years, about half of it would have decayed into other things. So if you have it would have half it would have decayed into bismuth 209, as you can see in the lower right hand corner. And different materials have different half-lives, or really how long, if left alone, they would spontaneously change kind of one atom at a time into its kind of daughter molecules or daughter atoms spontaneously, and leave about half of the mass remaining. And that's what would be defined as the half-life. Now, we have different isotopes of the same material, so the same elements, say carbon. We have carbon-12 and carbon-14. Carbon is determined by the number of protons, which is the atomic number. So every atom that has 6 protons is carbon. Now, but it can change by the number of neutrons, so that changes its overall mass, and it changes some of its nuclear properties. So, for instance, carbon-12 will not spontaneously decay into anything. Carbon-14 will spontaneously decay into nitrogen-14. And so some of the isotopes more easily decay than others. Carbon-14 is much more rare than carbon-12. Carbon-12 is what we have, but you could have sugar, which has a lot of carbon in it, C6H12O6. It has carbon in it, and you could have a mixture of carbon-12s. You could have carbon-12 and carbon-14s. You can have any combination. Chemically, carbon-12 behaves exactly the same as carbon-14. Isotopes behave exactly chemically the same. Some processes like evaporation and things there's a very slight difference that can be measured over time. But for the most part, they behave chemically in identical fashion. So how can we tell the age of something using the properties of radioactive isotopes? So imagine that we had 256 kilograms of carbon-14. And we know that carbon-14 turns to nitrogen-14 with a half-life of 6,000 years. Now, it doesn't just jump in half, so it doesn't like wait for 6,000 years and then you lose half of it. It kind of loses it one atom at a time at a rate that when you measure it in 6,000 years, you end up having half of what you had left. So if you start the clock at 256 kilograms and imagine that I capture the gaseous nitrogen-14, we go from 256 kilograms to 128 kilograms in 6,000 years, down to 64 and 12,032 kilograms at 18,000 years. So there's this clock, and pretty much if we can use this clock to determine the age of a material. So for example, pretty much this is what the method that we use. We have, if we know the half-life of a radioactive material, and we know how much there was originally. That's one trick that one has to be a bit more careful on. And we know how much there is now, and that's usually easy to measure. Then we can infer how old this thing is. Like for example, if I knew that there was 256 kilograms originally, and now of carbon-14, and now I have 64 kilograms, then I know that my sample had to be 12,000 years old in order to have two half-lives of 6,000 years. So that's the reasoning process. Now, knowing how much there was originally, that can be a little bit of a trick, and there are a couple of different ways of doing that. So the half-life of carbon-14 is 6,000 years. Carbon-14 decays to nitrogen-14, and we lose that. That's just a gas, and we generally don't have access to that. Carbon-12 is stable, which means that it does not decay. So imagine that I have 3 grams of carbon-14 in a material now, and let's say I know that originally there was 24 grams of carbon-14. What is the age of this material? I'm going to let you pause for a second. I'm going to give you the answer, but I want you to pause, work it out, and then see if your answer works with mine. Okay, we're back, and so this is the reasoning process. If I go from 24 grams to 3 grams, how many half-lives would I go? Well, one half-life brings me to 12 grams. The next half-life brings me to 6 grams. The next half-life brings me to 3 grams. That's 3 half-lives, so that would be 18,000 years. Now, usually we don't know exactly what's there originally, but I add another thing. So let's say that normally in a living material, for every gram of carbon-14, there's 10 grams of carbon-12, and carbon-12 is stable. Once it dies, then the carbon-14, starts to decay, or rather, it doesn't get replaced. So when the plant or animal is living, the carbon-14 ratio is being maintained by exchange with the environment. Once it dies, that exchange doesn't happen, and so the carbon-14 kind of keeps dropping down. Now, imagine that I have 2 kilograms of carbon-12 and 100 grams of carbon-14 in the material now. What is the age of the material? All right, now, pause it for a moment, and then I'm going to go through the answer and then see if it makes some sense. Okay, I'm back. Now, if I know that there's 2 kilograms of carbon-12 now, and carbon-12 is stable, that means I knew that there's 2 kilograms of carbon-12 originally in there, because carbon-12 does not decay. Then I know that normally for every 10 grams of carbon-12, there's 1 gram of carbon-14. Now, these are not the real numbers. The fraction is actually much smaller, but I'm doing this so that we can pretty much do the math in our heads. So a 10 to 1, which means if we have 2 kilograms, that means we'd have 200 grams of carbon-14. And if we have 200 grams originally of carbon-14, and now we have 100 grams, then that is 1 half-life, and I know that is 6,000 years. So in this way, and the only difference is in the quantities and the ratios, but the method is exactly the same. So here's another case where we might not know the original, and there's nothing in the environment that would give you that ratio. It's going to be different for different materials. However, if a rock is made all at once and it has several minerals, then it will have the same original ratio of its parent, and between the stable and the unstable daughter results from the process. So essentially, we have different types of lead, and I've actually there's a somewhat of a typo. It's not P2O6. Which would be phosphorus, I believe. It should be PB2O6, and in the table. What we have is we have several different minerals. They all started out with just the with some amount of uranium-238, some amount of lead-206 and 204 at the same ratios, and so we can then look at the fact that their ratios are all the same and at the beginning, and then differing amounts at any given time. And notice the years; these are in giga years, billions of years, and we're able to infer the age. And I'll give you a problem on this at some point later, so make sure you understand how this works. Notice at 0 years, all the ratios of lead-206 and 204 are all the same across all the minerals, but those ratios are different in the different amounts, simply because of differing amounts of uranium. And so then we get the uranium going to 206 and kind of going through that. When this is done with many different methods, different methods are different radioactive materials. They have different time clocks, and we have different amounts, different rocks, and so on. These are the estimates of the age of the rocks that we actually see. Pretty much 4.5 billion years is how old these rocks are, and it's consistent across different types of rocks, and it's consistent across different methods. So here we have independent clocks, independent methods saying that the Earth is 4.5 billion years old and more, in order to do that. Now, what I've been telling you about has been absolute dating. The geology and the cratering are done, they're what are called relative dating. Relative dating is when you don't have an absolute year to point back to, but you have, like, this one's older than that one. So with layering, the older ones are deeper, the younger ones are higher up. In cratering, that the craters within craters are younger than the craters around them. And so these are the sorts of relative dating. So what scientists use is to date any particular thing, any particular crater, any particular fossil, any particular thing, is layer in the Earth, is to do a mixture of relative and absolute time scales. So what we have is where we can measure, where we can do the radioactive dating, we use that, and where we can and where we can't, we use the relative dating in between those. So then we can kind of narrow the numbers between them, and this lets us give a chronology for events going back quite far. Now notice what happens. For example, these are, in geology here we have, millions of years. If I try to use carbon dating, which I showed before, which has a half-life of 6,000 years, if you waited a million years, there'd be no carbon 14 left in any no carbon 14 left in any material that you're looking at. So you do have to choose the clock appropriate to the time frame that you're actually looking at. So carbon dating can't be used for dating rocks. It can, however, and it's very useful in dating organic materials, especially those like paper, cloth, um, trees, those sorts of things. They're used to calibrate tree rings and tree ring data, which is used in climate as a climate proxy. Carbon dating has been used to demonstrate certain relics are, say, from the medieval period as opposed to from the Roman period, and so you're able to distinguish between things the resolution now is within several decades, and you can certainly tell whether something was made in, say, 1300 versus 100. And that's where carbon dating specifically is useful. But the actual mechanism, kind of the method for doing this, simply depends on the material that you use, the time frame that you're looking at, and the how quickly the clock itself runs. So our last part, we're going to talk about the age of the universe, and also, how we can verify some of these things. This is a spectrum from different galaxies, one that is close to us, one that is farther away, um, and it turns out that the one that is farther away is actually moving away from us faster because its wavelength is shifted. We can see the dark lines for hydrogen shifted over from where we would expect to see them in the lab, and we can compare them with what's in the lab. We see the exact same pattern, so we see the dark red line, the dark line in the red, the dark line in the blue, the dark line in the purples, and so on. We see that whole pattern shifted by the same fraction, and so that gives us a measure of its speed. And plotting the speed versus the distance, we find that the objects that are moving farther away from us, the objects that are farther away from us are moving faster than the ones that are closer. And this is the evidence for the expansion of the universe. And we can then, basically, because objects that are twice as far away are moving twice as fast away from us. If we played the movie backwards, it would bring all these galaxies to a single point, which would be the Big Bang. And we can find that out from looking at this, essentially just timing, speed and distance, and find the time. And we find that's about 14 billion years ago. So from these numbers, this lets us really determine the age of the universe. The methods we use even to get to that point, actually, because in order to figure out the distance to something that far away, we really need to piggyback on things. So, for instance, if I want to know the distance to let's say, the table in the room, I can use a ruler. But if I want to know the distance to, say, the car down the street, using a ruler is going to be kind of a drag, and so I'm going to need to have other methods. And then if I want to find the distance to, say, the planets, then I'm really in trouble, because then I'm not going to be going there. That's certainly not a convenient way to do it. But for example, so we start on the left-hand side with the things that are closest to us, and the way that we find the distance to, say, Venus is with radar ranging. This is the same kind of radar technology that is used to catch you when you're speeding. In this way, though, they send a beam of light out, bounce it off of Venus, and measure it when it comes back, and just measure how long it took, and that gives us the measurement. Of course, coming back, it's going to be much weaker, and there's some technology to essentially be able to boost the signal or be able to measure a very faint signal that is the reflection. So that's how we can get the distances to the planets. Now, how do we do the distances to the nearest stars? Because we can't do it that way. The nearest stars are 4 light years away, and there's no way we could bounce a light beam off of it. But it turns out that if you look at two objects from two different positions, you'll notice a shift relative to the background. So if you look at an object, and this is in the middle panel, where it says parallax, and what we see here is the sun is in the center, and we have the Earth on the January and July on opposite sides of its orbit. And when it does that, and we look at certain stars relative to the background, we notice a shift. Measuring that shift gives us a distance to, allows us to calculate the distance to different planets. This lets us figure out distances out to about 600 or so light years. So getting close to like 1,000 light years, and with very careful measurements. Uh, but even that, at some point, the stars are too far away. You just can't do that. So then you, the panels, the next two, in fact, next three panels, find correlations between certain properties, either temperature and mass, the period of oscillation of stars and its mass, or the and thus its light output of a star, and thus its distance. So if we know exactly how much energy is being cranked out, we can determine the distance that way. And so using the main sequence fitting, which is what we saw earlier, essentially knowing that brighter stars have a higher temperature, we can estimate temperature from the colors. We can get the luminosity, and then we can get the distance. Or if we use the period of oscillation of the luminosity, we can find that. Or the rotation speeds of galaxies, or the supernova explosions. And these are just a number of different, essentially, rulers that astronomers use in order to determine distance, and in order to get to determine the Hubble law, which is that galaxies that are farther away are moving faster away from us. Yeah. I'm going to finish with this picture, which is a part of the Hubble Ultra Deep Field. Every single dot in this picture, in this photo, is a galaxy. If we take, say, there's a lower right kind of yellowish swirl. If we take that galaxy, that looks like what our galaxy is. And we're sitting in our galaxy that has trillions of stars, and we're looking out to actually a part of the sky that has nothing in it, because if it had a star in it, it would completely blot out this picture. So the Hubble Space Telescope sat and watched for a week at a part of the sky that had nothing in it, and this is what you get. And this is a tiny, tiny part of the sky. What we have here are billions of galaxies in the universe. We have a small part of the sky that has hundreds. If we were to multiply it by the number of pieces of the sky, which is in the millions, we actually get billions to nearly a trillion galaxies. Each galaxy contains trillions of stars. Each star contains probably several planets, some of which might have life. And when you think of yourself on this tiny speck of the earth, and all the politics and wars, and all the fights and squabbles, and even all the accomplishments are all happening on this little speck in an unassuming little solar system, that it's one of trillions in an unassuming little galaxy called the Milky Way galaxy, which is one also of trillions. And it gives you a new sense of how vast and old and amazing this universe is. And the tools that we use to be able to take pictures like this, and to be able to infer our role in the universe, are related to the same tools that you use for estimating how long it's going to take you to drive to New York, or to know that the stovetop that's glowing orange is hotter than the one that's only slightly glowing red. And it's related to the fact that as an ambulance drives by, the pitch changes as it's driving towards you versus driving away from you. And all these tools that we learn in physics, and the energy and how conservation of energy and so on, They're all related. They relate the things on the earth to this vastness, which then gives you a new perspective on kind of your role in the universe. And it's worth pondering about. Thank you very much.